so far, we have learned that if you want to represent a physical system, there are two ways so far that you have learned, right? So a dynamic or a physical system when you want to represent it, so the first method that we learned is using basically differential equations, right? Using ODEs and PDEs in general. PDEs are partial differential equations, which we don't study in this course. We mostly focus on ordinary differential equation where your function has only one independent variable. That was one way. Now, if this ODE was linear and time invariant, then you could apply what? Laplace transform and then find the Laplace of output over input. So we call it what? A transfer function, right? That was a secondary method that you could show. So this one was limited to linear time invariant ODEs. And now today we are going to learn a third method, which you kind of seen when I was talking about ODE 45, but we're going to see it in a more formal manner and understand the meaning of those dummy variables and the stuff that we used. This method is called state space method. And the state space method also, here we just focus on ODEs, but the good thing about the state space is it is not limited to linear systems. So here the system with ODEs can be linear or nonlinear, the same with the state space. Okay, so here it could be linear or nonlinear. The same for here. This ODE is linear or nonlinear. So transfer function is limited to only linear systems. State space and ODEs are not. Now in ODEs, typically we use one higher or several higher order ODEs, like an nth order ODE, second, third, so on. In the state space, all of our equations are first order, so we have more equations. We have n first order ODEs. Okay, so as you saw in ODE 45, and we'll see how to represent it, what's the advantage, what's the meaning of each term here. So the first thing that we need to know is state. What is state? So a state of a system is the smallest, and I read it through the PowerPoint, but I'll explain it. It's the smallest, the minimum number of variables, we call them state variables, and the vector that has all these variables in it, we call it the state vector, such that if we know the value of them at time t naught at the beginning, then if we also know the forcing function of the system, the input to the system, we can find the behavior or the output of the system at any time point. Okay, what does that mean? So if we go back here and if we look at the mass spring damper example, so we had this mass and it was connected with a spring and a damper to the wall, right? And let's say there was no friction, so that is K, that is C. And then there was an external force F of T, and the output of the system is X of T. Okay, so my governing differential equation in this system, if you remember, was mx double dot plus cx dot plus k times x, assuming that damper and spring are linear, is equal to f of t. Now, I know the input to the system. I know my governing diffie q. Can I here solve for the output of the system at any time point? Can I do that? If I just know the input to the system and the governing diffie q, can I solve for the output of the system for any time point where t is bigger than or equal 0? Can I do that? No, I need two more pieces of information. What are they? Initial conditions, right? I need initial conditions. So I also need to know x at 0 and what? V or x dot at 0. So in order for me to find the behavior of the system at any time point, not only I need the input to the system, I also need to know the value of two variables, here position and velocity, at the beginning. Okay, so I call here x and x dot, I call them what? I call them the states of this system, because I need to know their values at the beginning in order to be able to completely solve for diffie q and find the behavior of the system in the future. Okay, so in this system, a natural choice for selecting states are position and velocity. Okay, now how many states do I need? Here it says the minimum possible. What is that minimum? The minimum is the order of your governing diffie q. Since the order of your diffie q is what? 2, then you need how many states? 2 states. Okay, so that's the point. Minimum is the order of the governing ODE. So we'll learn about the meaning of states. If we put them in a vector, then the resulting vector, we call it state vector. So here, if I define a vector z, or whatever you want to call it, and this vector has two components, x and x dot at any point, this we call what? The state vector. Right? And then the space formed by these two variables, so if I draw these two variables versus each other in a 2D space, so here is x dot and here is x, and t is actually an implicit parameter, right? Then if I plot this, correct? So it might look something like this, and then just keeps going, then that kind of space formed by these, we call it what? The state space. The space formed by these two variables as the axes of my basically coordinate axes, right? So that's the space here, state space. Now, why is it that we might choose state space over block diagrams and transfer function? Is, first of all, as I said, they work for nonlinear systems too. They are not limited to linear systems. And also, as we don't see it actually in this course. If you take an advanced control course, you see when we go to multi-input, multi-output systems, state space is way easier for analysis and design of control for multi-input, multi-output systems as compared to the matrix of transfer functions. Okay, so it turns out this is really much more useful than block diagrams and transfer functions. Now, one other important thing is, here, the states that we chose had physical meanings. One of them is position, the other one is velocity. not always you need to do that. Sometimes the variables that you choose for your states are not necessarily physically meaningful or measurable and or observable. So maybe some person comes and defines some new variables like z to be something like, and we'll see, we might need to do that, x of t plus f, where f is the input, and then the second one is something like x dot of t plus another number like a, and this also times a, a1, a2 times f dot of t. Okay, so I'm adding position and force together. Well, can you do that? Of course not. Unless these A1 and A2, they have what? They have units, okay? So these guys have units. So for example, if this whole thing has unit of length or meters, let's say, then I can say that A, right? So this is unit of meter, this is unit of Newton. Then I can say this guy has unit of what? Meter over Newton. Or here, this one is meters per second. This is Newton per second. Then again, I can say this has the same kind of unit, right? Meter per Newton. So these are not just constant numbers without units. They have units, but sometimes we need to combine states and the meaningful states and inputs, and then call it new states. Now these are clearly not super meaningful and not measurable. Why do we do that? We'll see later, okay, why. But note that although most of the time we try to choose meaningful and measurable quantities as our states, not always that is what we do. Sometimes we choose unmeasurable or non-meaningful quantities as my state variables. Okay, now I mentioned that the space formed by these state variables, we call it the state space. Now, what's the importance of this? Why should we plot these versus each other? What does that tell me? So let's first learn about the importance of that, and then we'll go about how we create this state space representation and how to go from block diagram to here and vice versa and so on. So what's the importance? What do we learn? First, the area contained within the state space plot represents the total energy, mechanical energy of the system. In other words, kinetic energy plus potential energy. Okay? So let me go through a simple example first. So the simple example I want to mention is the mass spring only. So if I have the mass and spring only, nothing else, no forcing function, no damper, nothing. So no energy is injected into the system because of the external force, and no energy is wasted in the system because of damper. So you just give it some initial position and then release it from rest. So your initial velocity is 0, but your initial position is non-zero. So you just, it's like a pendulum also. You move the system away from the equilibrium and let go. And what you will see is the system will start to what? Oscillate forever, has sustained oscillation. So the governing equation here is mx double dot plus kx equals 0. And with those two initial conditions, if you solve for x of t, you can easily show that x of t is going to be x naught times cosine of square root of k over m times t. Okay, that is going to be your solution, where x naught is the amplitude of the oscillation and the square root of k over m, the whole thing is under square root. We call it natural frequency of the system. Okay, this is the frequency of the oscillations in radians per second. You'll see that in your vibrations course. So that's your solution, fine. And then if you take a time derivative of this, your x dot of t, that guy will come out. You will get negative x, and let me call this omega n, if you don't mind, natural frequency. So it's going to be negative x dot omega n times sine of omega nt. Agreed? Now, if I divide x of t by x naught, and then square it, and then divide x dot of t by x naught times omega n, and then square it, okay, this is going to be what? It is going to be cosine squared of omega nt plus negative sine of omega nt, the whole thing squared, which clearly it is going to be 1. So what does that mean? Since this is one of my axes, x, and the other one is x dot, so if I call this constant a, and if I call this other constant b, right, then if I call this x and if I call this y, because they are my x and y axes, the equation will be like x over a squared plus what? Y over b squared is equal to 1. What kind of shape is this from your geometry knowledge? Yes, that is in what? That is an ellipse. Okay, so in this system, if I plot the state space, right, if I plot x dot versus x, what kind of shape do I get? An ellipse. Something like that. I will get an ellipse centered at origin, right? Where here, this is x naught, and this is x naught times omega n, and here I assume omega n is less than 1. If it's more than 1, then the ellipse will be longer in the x dot in the y direction. Okay, so it's going to be a closed curve. That is the curve that I will plot, and I can show you in Simulink. That's not a hard deal. You can plot this, and if you plot that in Simulink, then you see that it is going to be a closed curve. Now, as I said, the area inside this area inside is a representation of the energy of the system. And since this area does not change, it means what? It means that the total energy of the system is going to be conserved. It is going to be constant. Is that the case? Yes. We know when you learned that in your dynamics, right? Conservation of energy. So if there is no element that is non-conservative, there is nothing that injects energy or wastes energy, then the total energy stays constant. Potential converted to kinetic and kinetic converted to the potential, but the total sum is not going to change. And that tells me that is the case actually. Okay, so you see it completely makes sense. It's completely meaningful, right? So let me do that very fast just so that we have a small practice on Simulink as well one more time. So I'm going to simulate mx double dot plus kx equal 0 for you, subjected to 2 initial conditions, and then plot x dot versus x so that you see the behavior of the system. The first time you launch Simulink, it is a little slow to load the library and everything, but after that it is typically very fast. Okay, so while this is gonna go up, so this is the first case that I mentioned for you where the total energy is not gonna change. Now I can easily show you that if you add a damper to the system, then the state space curve would look like a spiral that ultimately will converge to what? To the origin. Really? Yes, it does. It actually does. It will be converted to the origin. Why? Because the damper eats out the mechanical energy and converts it to heat that I cannot get back because of generation of entropy. So the energy of the system goes, and the area confined by the curve ultimately goes to 0, so you're going to lose all the energy. On the other hand, if you have an external force that injects energy into the system, if you start here, then it's going to be an outward spiral, and you get more and more energy if it is not balanced by a damper or something, and ultimately your system will go unstable and your energy goes infinite. Okay, so let me show you a case here. So what we need is an integrator or two integrator blocks. Then we need a gain, and then we need the scope block, and I guess that's it. I add one more of that, right? So this is x, this is x dot, and this signal here is x double dot, and x double dot is negative k over mx. So if I bring this guy here and I call this gain negative k over m, then I can get my x double dot, right? And here I assume that k is, just give it a number, 10, and then m is 2, okay? Or let's use some good numbers so that the natural frequency is a round number. So 18 over 2, 9, square root of that is 3, right? And then I apply my initial condition. So this is initial velocity, it's 0, and this is my initial position. Let's say that is 0.2. Okay, and then I go here and make sure I will get a smooth plot. So I increase my sample time from -1, which Katia, sorry, I'm teaching so many software, I'm just messed up. MATLAB decides I will tell it every 10 milliseconds. And now let's go here. Right, so this is what? This is going to be x versus t, but that's not what we want, right? Sustained oscillation. What we want is we plot x versus x dot. So in order to do that, under sinks, you bring this guy called xy graph. Okay, and here, instead of doing this, you will bring your x-axis and your y-axis. So my x-axis is going to be x, actually. And then here is going to be x dot. Okay, so I'm plotting x versus x dot, and now you do it, and there we go. Here we go. Okay, so easily you can see that. Again, here I guess the sample time is not really good. Let me increase that, do it one more time. There we go. Perfect ellipse. Now here, since natural frequency is more than 1, the ellipse is elongated along y-axis. It's 3 here, actually. So this axis is 0.2, 0.2, semi-minor, and semi-major is 0.6 and 0.6. Okay, so very easily you can see that, right? When you have a what? You have a mass spring system. Now I want to add a damper. So this time your equation will have one more term in it. This time you have mx double dot plus cx dot plus kx equals 0. Therefore, your x double dot, as I said in Simulink, you have to calculate the highest order derivative based on everything else. So it is going to be negative k over mx and negative c over mx dot. Okay, so I need to implement this equation in Simulink. So I need to add the stuff, so I need to bring the sum block. Now both blocks are negative, but I can implement the gain to be negative, or I can implement here to be negative. So I can say negative, negative, then here I make this positive, okay? So, and then call this k over m. So what I need here is negative k over mx goes here, and then another one goes there, and this one is C over M, and C over M is multiplied by X dot. And then here I say C over M, let's use a number like 1 here, not a big one. Okay, and that's it. Okay, so now this signal is what? X2 dot, this is X double dot, which is negative CM X dot, right? This should be, I don't need that. So C over MX dot, and this is K over MX. Some of them is, if you want to write it, I can write it for you, but we don't really need to. So this is KX over M, and this is C X dot over M. C times X dot over M, and this is K times X over M. Okay, and now let's do it again here. Yes, I guess now you can easily see the spiral, and the system energy is being wasted. If we continue a little bit more time, the time is implicit here, okay, you cannot see it, then it will ultimately would stop, right? If you look at the X behavior, it is a damped oscillation, right? It is an oscillation that will fade away and goes away, right? So you can look at this if you want. It's called underdamped behavior or damped oscillation. So here we go, right? This is this one, and this is your damped oscillation. Okay, so I guess now you understand the meaning of this state space, and that is a very good tool for analyzing and visualizing the behavior of the system. Good. So now that you are motivated, let's talk about how we can get this representation, because we know about transfer functions. What about this? So here I do it first very general. Assume that your system has R inputs, so it's a multi-input, multi-output system. First we do it general, then we go to single input, single output for most of them. But let's say your system has R inputs, it has M outputs. You show your outputs by Y, you show your inputs by U. Okay, so you have M outputs, R inputs, and then the states of the system are N. So you have N states here. Then the goal is, in general, to come up with two sets of equations. One, sets, and these are vectors. One, first order differential equations, we call them state equations, or state equation, in which you show how these state variables change versus time. So you calculate the first time derivative of each one of these states as a function of what? The states themselves, the inputs, and potentially time, if your system is time variant. And then you show also that your outputs, each one of them, is a function of what? The states, the inputs probably, and what? Again, potentially time. So the goal is to form a bunch of output equations and a bunch of what? State equations. Once you figure this out, that's over. Now, this two here, functions f and g, can be linear or what? Non-linear. If your system is non-linear, then f and g will be non-linear in general. If system is linear, then instead of writing it like this, I can actually write those equations this way. I can, assuming that the equations are linearized and time invariant. So assuming that the time is not there, then you can write your equation into a matrix format, where the first derivative of vector x is a matrix A, we call it a state matrix, times the vector and plus another matrix P, which we call it input matrix, times the input vector. Then your output vector is a matrix C times the state. We call it basically the output matrix, and then another matrix D times the input, which we call it direct transmission matrix. Okay, so this is what we're going to do in this course. We use linear equations, but in general you can do nonlinear and write them this way. Okay, now it might not be easy to digest in the beginning, so what I want to do with you is we go through an example, and then step by step I'll show you the meaning of each and every one of those formulas. So the system here that we are going to focus on is the simple mass spring damper system that we had. So the mass is connected to the ground with spring and damper and mass. There is an external force U that is applied to the system, and then the position of the system measured from equilibrium. So first you let it come to equilibrium, then you apply your input force and measure Y. So Y is not measured from initial position. It is actually, it is measured from equilibrium, and I'll tell you what's the importance of that. If that's the case, then your governing equation in the Y direction will be similar to what we had in the X direction. My double dot plus By dot plus Ky equal U. Here I call damper constant B instead of C. Doesn't change anything. And you might wonder, where is the gravity force gone? Shouldn't it be also included here? No. That's why I said it starts from equilibrium. Okay, so basically when you let the system go to equilibrium, this mass, since it has gravity, it will cause this spring to be stretched, and the amount of spring force, K times the initial stretch, delta, whatever you want to call it, should be equal to mg, so that this system is at static equilibrium. So initially this spring is stretched, amount of delta, which is equal to mg over k, to keep it in equilibrium. Now from this point on, if you push mass m further, you call that extra displacement y. Therefore the force in the spring is actually k times what? Whatever delta was plus y. So if you draw your free body diagram, you have by dot here, you have mg here, and then you have k times delta plus y up there, plus of course u. So as I said, for equilibrium you needed that k times delta to be equal to m times g, okay? Because when you are at equilibrium, the system does not move, so the damper does not apply any force. The damper applies a force only when you have velocity. So this equality exists, and u was not there in equilibrium, so the system comes to equilibrium on its own. Therefore, here, if you write this as k times delta plus k times y, expand it, these two will cancel out. So when you write your governing equation, it will be my double dot is equal to u minus ky minus by dot, with y being downward. And then when you bring these two guys to the left, then there is no mg left, because mg is already canceled with the spring force, excessive spring force due to initial extension. Okay, so don't be surprised if you do not see mg here in your equations, and do not add that. If you ever see a vertical oscillation instead of horizontal, do not jump ahead and directly add mg. Make sure that you consider the initial stretch of this spring. Okay, so that's my equation. So this is a physical system. The input is the input force u, and the output is the position of the object y. Yes? Now we want to find the state space representation of the system. The governing equation is time invariant and linear, so my goal is to first come up with some state variables and then write my equations of state and output in this format, in this matrix format. That's the part that you need to know linear algebra, okay? Although it's not really advanced linear algebra, but you need to know very basic of matrices. So we'll do that, and then I'll show you if the equations were nonlinear, I can write it this way. Okay, so let's get started on that. So here what I have is my double dot plus by dot plus k times y is equal to u. And I know u is the input to the system and y is the output of the system. So I know these. So first I need some state variables. How many? As many as what? The order of the dpq, which is 2. So I use a state vector z or x or whatever you want to call it. Let's just call it x, similar to our notation. And this should have 2 variables in it. Which 2 variables do we choose? Similar to the horizontal oscillation system that I mentioned, our natural choice here will be the position of the object and then what? The velocity of the object. We can choose any that we want, but these are typical and they have meanings and they are measurable. Okay, so that's my x. Good. Now I take a time derivative because my goal is to find vector x dot. As you can see here, for the first equation, the goal is to find x dot, and here x is a vector, right? Vector of all variables. So what is it going to be? If I take time derivative, your x dot is going to be y dot and what? Y double dot. Is that true? Yes. So I leave y dot as is. What is y double dot? How do I find it? As I said, you always find it from your governing equation. Just like what you did in Simulink. You find y double dot based on everything else. So what is y double dot here? Y double dot is going to be 1 over m times u, right? Or if I start from the y, it's going to be negative k over m times y, negative b over m times y dot, and plus 1 over m times u. And now I just write it down here. Yes? Now, this is the part that I'm trying to do it in a matrix format. So here, if I just basically want to write it in that format, I can say that x dot is equal to some matrix A times x, correct? And x itself is what? Y and y dot, correct? And plus some other matrix B times the vector of inputs, but here you only have one input, so that input is u, so you just write u. Okay, so you don't have a vector of u's, you just have one u. Okay, so this guy, which is equal to y dot and y double dot, this I want to write it as a matrix times itself, right? Where this one we call it A. This is the vector x itself, and this is B, and this is u. Now here I only have one u, so The scalar u and the vector u are the same thing. Now, how do I fill these matrices? First of all, what is the size of them? If I know their size, it helps a lot. And then I fill them. So let's look at the sizes. So here, my x dot and x, as you can see, both of them are what? They are 2 by 1, right? They are 2 by 1 vectors. So this guy is a 2 by 1. This guy is a 2 by 1, and this is a 1 by 1, right? It's a scalar. So now what are the dimensions of these matrices, right? So what is the dimension of A? What is the dimension of B? So what should I multiply by a 2 by 1 to get another 2 by 1? Of course, the dimension is what? 2 by 2. And what should I multiply by a 1 by 1 to get a 2 by 1? Of course, a 2 by 1. So A is a 2 by 2, B is a 2 by 1. So what is it? Let's see. So what is the first row? The first row here should be such that when I multiply that first row by the x and then add that to the first element of B multiplied by u, that whole thing will be what? Y dot. Right? So if you look, y dot has how many y's in it? If I multiply anything other than 0 by y, then I have something times y plus something times y dot plus something times u. That is not going to be equal to y dot. So all I need is I multiply a 0 by y, I multiply a 1 by y dot, and I multiply a 0 by u, right? If you just carry that, 0y, 1y dot, 0u. So it's going to be y dot equals y dot. Life is good. Actually, I can write this way if you want. I can write this top row like this. I can write it as 0 times y plus 1 times y dot plus 0 times u, right? I can write it that way. That's how you write y dot. And then, so if you look at these elements, 0, 1, and 0, these are here. That's 0 and 1, and that is the other 0, correct? Now, how do I write my second? So y double dot is negative k over m y, so I have to multiply y by negative k over m. Then I multiply my y dot by what? Negative c over m, and then multiply my u by 1 over m when I do the second row times x plus the second element times u. The result of that will be what? Y double dot. So now this is my matrix M, this is my matrix B, and this equation is my state equation, that x dot is A times x plus B times u, where A is this and B is this one. So I could write my first equation. Now I go to my second equation. The second equation is the output equation. So I have to write my output as a matrix times state vector plus another matrix times input vector, right? So here, my output vector y is simply the y itself. The only output I have is position. I am not looking at any other output. This should be equal to a matrix times the position vector, the state vector, the state vector, plus some other matrix times u, right? Where here, the output is just a 1 by 1, the input is a 1 by 1, this guy is a 2 by 1, right? So this matrix that I call it C and this matrix that I call D, if I want to find their dimensions, what should you multiply by 2 by 1 to get a y by 1 by 1? Clearly, it's a 1 by 2. And what would you multiply by 1 by 1 to get another 1 by 1? Of course, a 1 by 1. So what should I multiply by this, and then what should I multiply to u to simply get y? Well, of course, I need to multiply a 1 times y. There is no y dot, so I can write it as 0y dot, and then what? 0 times y, right? Because I can write this guy as what? 1 times y plus 0 times y dot plus 0 times u. So I can use 1, 0, and 0. And that's how I form my two equations, right? So this guy here, this thing that I'm drawing for you, this is the state space representation of this system. Okay? So I wrote them for you. Now, let me add those dimensions here, right here for you, so that you always know the dimensions of these matrices. So in general, not always you only have one input and one output. When you have more than one input and one output, then these we'll do more in class. These are going to be a little more complicated. But in general, as I said, if you have n state variables, r inputs and m outputs, then I can add some dimensions for you here, okay, to make it nice. So here I typed the dimensions of each one of these matrices. A is n by n, B is n by r, C is m by n, and D is m by r. And this would hopefully help you better. And this is a block diagram for this system. So what you have is, if you have x, you can multiply it by a. If you have u, you can multiply it by b, add them together, so you are forming this top row, and the result is going to be what? X dot, and then your x dot, if you integrate it, you will get what? X. Then if you multiply that x by c and multiply u by d and add them together, what would you get? You will get the output y. So this block diagram exactly represents these linear equations for a state space, right? So it's quite clear, as I said, we need to solve more examples in order for you to master this concept. But now, just to mention that this guy works, this method works for nonlinear systems, I want to show you what happens if one of these terms or several of these terms is nonlinear. Okay, what does happen? So what I would do here, I use a nonlinear mass spring damper system where my double dot plus by dot squared plus k1y plus k2y cubed is equal to 0. So I use a nonlinear spring, and I use a friction term that is due to air drag instead of viscous friction. Okay, so this is completely nonlinear. I cannot apply Laplace to this and make a transfer function, but yet I still using the same variables I chose and see equal to u. Actually, let me add an input, because you need to have an input in this method. And again, this guy is the output, this guy is the input. The order is 2, so again I choose 2 variables, and y and y dot again are good choices. Now if I take a time derivative from here, x dot is going to be y dot and y double dot. Y dot, I write it as is, no difference. Y double dot, I'll find it from this equation. It is going to be basically k1 over m times y with the negative sign, negative k2y cubed over m. negative by dot squared over m and negative or positive u over m. Now here, clearly I cannot write it in a linear format anymore, but all I need to do is to write it as a function of x, u, and t. Now here I don't have t, but I have u and x. So all I would do is I would say x dot can now be written as, and these are actually those functions, as simple as that. X dot can be written as a function f and pay attention, this is a function. This function is a vector function, so it has two functions in it. It's a function, it is going to be a function of x and u and t, but here our x is simply y and y dots, and u is a simple u, and there is no t. So if I write it this way, that is going to be fine. Now, as I said, this f has two components, so I can write it as f1 of y and y dot and u, and f2 of y and y dot and u. What are those functions? These guys up here. So this is f1, this function. The general function between y dot and u is simply y dot. And then f2 is this function. It's a nonlinear function of y dot and u. That's simple. And then output here, y is going to be another function, g of y and y dot and u, and it's simply equal to y. Okay, so your g is simply equal to what? Y. That's it. So I know my functions. Okay, so nonlinear case is actually easier than linear because you have to format them all in matrix notation. Okay, so this is how to find the state space representation of the system. Now, I learned that there are three ways. And I know how to basically go from ODE to state space and how to go from ODE to transfer function, right? So I learned those. When I want to go from differential equations to transfer function, what do? I apply Laplace transform. When I want to go back from transfer function to differential equations, I apply what? Inverse Laplace. We have done that. Now, when you want to go from differential equations to state space, I use what? I use dummy variables or state space variables, if you want to call them, right? And I can go from differential equation to state space. Can I go back from state space to differential equations? Yes. I have to substitute and eliminate these dummy variables. Let me show you this, and then I'll show you how to go between transfer function and state space, back and forth. So if I know now these guys, correct? I have these equations. How can I go back from these back to this one? Well, that's not a big deal. Let's see how. So what I have is, I have y and y dot is equal to. Or actually y dot and y double dot, which is the vector x dot, correct? This is equal to a matrix A times x plus a matrix B times U. And this was 0 and 1. That was negative K over M and negative B over M. Actually, in this case, if you know this, you do not even need to do any elimination. All you need is just look at this last row. If you just expand this last row, that's your governing DPQ, right? If you do it, you're going to get Y double dot equals to negative K over M Y negative B over M Y dot plus 1 over MU. Just multiply both sides by M, bring the negative terms to the right hand side, and you will get what you had in the past. Okay, so it's not a big deal. It is basically hidden inside your state space. Typically, it's the last equation if you choose your state variables the same order that I said, y and y dots, position, velocity, for a mechanical system. Okay, so it's not really hard, but the thing that I mentioned is for the case of calling these, instead of y and y dot, I would call them two dummy variables, x1 and x2. If I call them x1 and x2, then I need to do elimination, because now you have these equations, that x1 dot is x2, and x2 dot, if you expand those, is going to be negative K over mx1, negative B over mx2, plus 1 over mu. So here, you just need to take basically the time derivative from this. So you're going to get x1 double dot is equal to x2 dot, but x2 dot you plug it back from the bottom equation. And for x2, you replace it with x1 dot and 1 over mu. And if you see here, this is, if I just neglect this for a moment, that is your governing equation if you just replace x1 with y. So that's the substitution and elimination. It's the same things, no big deal. Okay, now what I want to talk about is how to go between transfer functions and state space and backwards. Going from state space to transfer function is actually very easy, and there is a unique solution to that. It's very easy. We apply Laplace transform, and there is a unique formula for that, which I'll show you. If, on the other hand, you want to go from transfer functions to state space variables, there is no unique solution. There are infinitely many solutions in general, depending on what you choose as a state variables. There are forms that we prefer. We call them canonical forms. I'll talk about this very fast. Okay, so here is, these are those canonical forms, and I'll talk about them, but let's first talk about this. So if I have state space, how do I go to transfer function? Well, it's not a big deal. I have my state equation. I apply a Laplace to it. If I apply Laplace, Laplace of x dot is going to be sx of s minus x at 0. And then Laplace of ax plus bu. Now here, remember, when we do Laplace transform, we will choose our initial conditions to be what? 0 when we are looking in finding a transfer function, right? So this guy ought to be what? 0, right? Because we are looking for a transfer function. So 0. It's a vector 0, and I'll put it up here for you. So we choose 0 because we are looking for transfer function. If you do so and factor out x of s on the left side, you're going to get x of s, right, times, and then you have a here. If you bring it to the left side, let me do it for you here. So you have x dot equals ax plus bu. I apply a Laplace to this. It is going to be s times x of s, and here this x of s is a vector, minus x at 0, here is the time vector, is equal to a times x of s plus b times u of s. Okay, again, these are vectors. We choose 0 initial conditions because we are looking into transfer functions. Then I bring this a here. This is a matrix. This is a scalar. I can simply write x here to be I times x. I to be identity matrix, and if this guy is n by 1, this is an n by n identity matrix. We know when we multiply identity matrix by any vector, nothing is going to change. So if I do it then and bring this term here, it's going to be si minus a times x of s is equal to b times u of s. And you might ask me, why did you multiply it by I? Because here I cannot simply subtract a scalar s from a matrix which is n by n, right? I cannot just subtract scalars from matrices. If this guy is n by n, I need to subtract an n by n matrix from that. Since this I is n by n, I just multiplied by s, so all diagonals instead of 1 will be s, everywhere else 0. Now I can subtract two similar matrices. And now I multiply both sides by the inverse of this matrix. So you will get x of s to be what? Inverse of this guy. Correct? Times b times u of s. Okay? Now y of s is equal to c times x of s plus d times u of s, right? If you just take a Laplace from the output equation, right? Your output equation is this one. I take a Laplace, I'll get this. And now this x I found in the earlier stage, I replace it here, correct? So I bring that thing right here. And so you have something times u of s, another thing times u of s. So you can factor it out. It's going to be this big matrix times u of s. What is that matrix? It's going to be c times si minus a inverse b plus d. So y is that times u, and then the transfer function g, which is y over u, is going to be this guy in brackets. C times si minus a inverse b plus d. Okay? So if I plug in my A, B, C, D matrices into this and calculate it, it should give me back my transfer function. Really? Yes, let's plug it into the examples that we just did. Remember, in this example, we found A, B, C, D to be these matrices. So I'm going to plug them into that formula and simplify and see if I get a g of s here. By the way, what is g of s? I can just do g of s directly from here so that I have something for comparison. So if I wanted to directly get my transfer function, I have my double dot, correct, plus by dot plus ky equals u. If I apply Laplace directly here and I use initial condition of 0, I will get ms squared plus bs plus k times y of s is equal to u of s. Therefore, my transfer function should be output over input. It is going to be the second order system. Okay, so this is what I should get. Now, will I get that if I apply that formula? Well, let's see. It was C times Si minus A inverse B plus D. Now, C was basically 1 and 0. B was 0 and 1 over M, and D was simply 0. A was 0, 1, negative K over M and negative B over M. This is the I matrix, 1, 0, 0, 1, and you multiply it by an S. Right? So let's simplify. So there's going to be 1 and 0. Then inverse of, so when you multiply S by this, S is multiplied by each one of the elements, and then you subtract. So the resulting matrix here is going to be basically S, negative 1, K over M, and S plus B over M. And then you multiply that by 0 and 1 over M. And that D is nothing, so just neglect it. Now here is the part that you need to invert a 2 by 2 matrix, and hopefully you all remember how to invert a 2 by 2 matrix. If you don't, I write it for you here. Please do not forget it. You need that in this course. So if I have a matrix with 4 entries, A, B, C, and D, the inverse of this is going to be another 2 by 2 matrix divided by the determinant. Determinant is diagonal product, AD, minus anti-diagonal product, BC. Now what would you do here? You swap the diagonals, so D goes here, A goes here. The anti-diagonals, you just negate them and keep them in place. Okay, so that's your inverse. So basically each one of these entries have to be divided by what? AD minus BC. So that's the inverse of a 2 by 2. So now if I go back here, this matrix has a determinant, which is S times that minus negative 1 times that. And then you swap. So if I proceed, 1 and 0. This is going to be a 2 by 2 matrix divided by determinant. So minus 1 is going to be plus 1. Here you exchange, swap. These two you just negate. Right? And I guess you can do that now. So the first thing you can do is you multiply this by that. So here, when you multiply this by the first column and then by the second column, since this is 0, you only will keep basically the first row, okay? The first row remains, the second row goes to 0. So if I multiply these two together, the result is going to be just the top row. Then I multiply that by this one. And the whole thing is divided by the determinant, which is S squared plus B over MS plus K over M. Okay, and now if you multiply a row by a column, that will be multiplied by the 0. This will stay, so it's going to be 1 over m divided by this. And if you simplify the 1 over m's, you will get exactly what you have. Okay, so there should be no difference. You should exactly get the same thing that you did by applying Laplace to your differential equation. This formula should give you a unique solution, and they should be the same. Okay, so we applied that. Now, as I said, when you want to go back, so you have your transfer function, and you want to get A, B, C, and D. Okay, so I give you this. I say this is my g of s. You tell me what is A, what is B, what is C, what is D. There is no unique solution. There are infinitely many solutions. Why? Because depending on how you choose your state vector, your final answers could be completely different. Now, among these infinitely many different answers, ideally, which one would you choose? There is a category of them, we call them canonical forms, and the canonical forms are the ones we prefer. Now, what does that mean? So canonical forms are typically the forms that have the maximum number of zeros and ones, and their matrices are mostly triangular, upper triangular, lower triangular. Okay, so they try to basically maximize the number of zeros, make matrices basically what we call sparse matrices. So, or as much as possible. So now there are two ways to get the canonicals. There are two scenarios. Scenario one, the transfer function that you have, there is no numerator to that. It's just 1, like this example that we have. There is no linear term or anything in the numerator. It's just simply 1. That is the easiest. When that's the case, what you need to do, as I said, you just start. You consider your output to be the first state, the first time derivative to be the second state, and keep going if your ODE is higher order. So if it's just second order, you just need 2 of them. If it's 10th order, you need 10 of them, right? So each time that you go to the next variable, you add 1 more time derivative. Second time derivative, third time derivative, all the way to n-1 time derivative. And if you do that, then your matrices will be just this simple. First row is 0, 1, all 0. Second row is 0, 0, 1, 0. So it's just 1 column shifted. You go all the way. The n-1 row is just all zeros except for last one, which is 1. And then the last row are the coefficients of the denominator. The last row are the coefficients of the denominator with a negative sign starting from the constant term all the way to the last but 1. So you go backwards and you all negate them. And the other thing that you need to have here, which is important, is this first term should be 1. If it's not 1, you have to convert it into 1. I'll show you how. B is going to be all zeros except for last one, which is a 1. C is 1, all zeros. D is 0, right? Really? Yes. Let's find that. So let's see if what we said here can be applied to this example, right? So in this example, I say, well, my transfer function is this. G of s is equal to y of s over u of s, and it is equal to 1 over mss squared plus bs plus k. Numerator does not have anything, it's just 1, but the leading term of the denominator is not 1, it's m. So what I will do first, I will divide both numerator and denominator by m. to make that leading term 1. You have to have that. Otherwise, this method does not work. So now you will get 1 over m divided by s squared plus b over ms plus k over m. Now the leading term is 1. Good. The denominator is not 1 now, it's other than 1, but still constant. There is no s term in it, so we can still use it. Now this method says first of all, how many variables you should choose? As this method says, you should just choose as many as the order of the ODE or the order of the denominator polynomial. So your polynomial here is order 2. Therefore, you just need 2 variables. So what you would do is you say my x1 is y, the output, and my x2 is the time derivative of that. So this is going to be my state variables. Okay, so this is for this part. Now it says A is, as we know, it's just a 2 by 2 in this case. So if we go follow this, you just need to focus on the 2 by 2 portion of it. So what you really need is this part, and then basically this part. So the first row is going to be 0 and 1. The last row is going to be negative an, negative n minus 1. Where what is an, what is an minus 1? Let's look at this. So let's borrow this as well. So here we compare these two together. The denominator of this and this denominator, right? So what do I get? So if you see here, the coefficient of the highest term is 1. The next coefficient here is a1. The next coefficient is a2. Here, n minus 1 is just what? Because n is 2, so you just go to a1, right? So what do you need? Which coefficients do you need? You just need basically an and an minus 1, right? As I said. So you just need this term and this term. So you just need to look at this guy, that is your an, and then this one, which is your an minus 1, and negate them both. So this is going to be negative last one. As I said, you go backwards from the last one to the first one, to the first one but 1, first but 1. So it's going to be this one negative, then it's going to be the next one negative. Is that the same a that I got last time? Yes, it is. You remember, that's the same a. Now, what about b? So it says b is all 0 and 1. Now, here is the part that you have to pay attention. So b, in our case, is not going to be all 0 and 1. Why? Because this is assuming that the numerator was 1. Now that your numerator is 1 over m instead of 1, okay, you can bring this 1 over m here actually if you want and say y over 1 over mu is this. So your input, you can consider it instead of u to be 1 over m times u. So whatever you have other than 1 here, you multiply it by b. So your b is actually going to be 0 and 1 over m. Is that the same? Yes. If you remember, b is 0 and 1 over m. Then it says c is all 1 and 0, and I guess that's the case because our output is still y. And I only have 2 of that. If you remember, it was a 1 by 2. This one was a 2 by 1. And then d is simply a 1 by 1 and it is 0. That's the case here. Right? So you see that's our C and D. So I can directly get them without any problem. So again, canonical form, in case the numerator does not have any S term, it is quite simple. You have to keep in mind that the leading term of the denominator should be 1. If it's not, you divide, and then if you divide, anything other than 1 will be multiplied by matrix B. Okay, so let me just mention that for you somewhere here. So I have added this explanation for you. Actually, if matrix D is anything other than 0, in this case it is, so you don't need to really multiply. So I can take this off. But if matrix D was anything other than D is 0, then you have to multiply matrix D by that factor too. But here, since it's 0, you don't have to. So I just added this explanation so you don't get trapped. Now, the hard case is when there is numerator dynamics. There is S term, or there are S terms in the numerator. So your numerator is actually not 0. Still, the leading term in denominator is 1, but your numerator has time derivatives. There are time derivatives of input in your numerator. In that case, it is not going to be as easy. Okay, so I'll explain that here. So in this case, you know, the transfer function is simply 1 over s to the n plus a1, s to the n minus 1, and so on. Let me actually add that as well for you. So instead of the dfq's, I replace them with the corresponding transfer function, right? So here, this is the case that the leading term is 1, numerator is 1. Here is the case that the numerator has a lot of S terms in it, or a few S terms, at least one. It's not just constant. In this case, as I said, choosing the state variables is not as easy. What you need to do in this case is your states are going to be a combination of output and input. Remember, I told you in some cases we have to combine input and output, and they are not necessarily meaningful nor measurable. That's the case. And these betas, they all have units. So here I'm combining my output y with a coefficient beta times u. Then the second vector is first time derivative of output plus another combination of what? First time derivative of input plus the input. X3 is second time derivative of output plus a combination of input, first derivative of input, and second derivative of input. So it is quite complicated, but these betas you can find from A's and B's, the coefficients of numerator and denominator, and then if you do so, only if you do so, then you can get your matrix A to still be canonical, C to be canonical, B and D. B is not going to be a bunch of zeros this time. It has numbers, the last one, everything, and D is not going to be 0 as well. Okay, so I can give you an example of this very fast. So let's close a few of these. Okay, so this is our choice. This is what we are going to have for A, B, C, and everything. And this is going to be your governing ODE, or you can say better, it is actually your transfer functions. Function, not functions. Okay. Right, so Let's go as big as possible. There we go. Right. Now let's just get an example here, and here I would go with g of s to be similar to last time, so s squared, and then I use some numbers for b and k, so let's say 2s plus 3, and then here I add one linear term here, like s plus 1. In this case, it's not as easy as, and I say this is y over u. I cannot simply choose y and y dot to be my state vectors. It's not going to be that simple. So I go with this selection. I just need two of them. So I just select the first two. So I say my x1 is y minus some beta naught times u, and my second state variable is y dot minus beta naught, the same thing, this time times u dot, and a new variable beta 1 times u. But first I need to find beta naught and beta 1. Okay, so what are these? So we go according to our equations for betas, right? So what are these betas? We bring them from the lecture, and says here is how you decide your betas. So beta naught is b naught, and b naught is the coefficient of the highest term with the same order as the highest term in denominator. So here, if you have s squared, do you have s squared here? No. So actually, you can write the numerator here as 0 times s squared plus what? 1 times s plus 1. There is no matching s squared here, so b naught in your case is what? 0. Therefore, beta naught is the same as b naught, right? Correct? This guy is your b naught, the coefficient of the highest term, which should match the denominator. So this is your b naught, and this is the same as beta naught. So this guy is 0. Therefore, your first variable is simply y. Okay, and then this one is 0, so that makes life easier. But now beta 1 is b1 minus a1 beta naught. So since beta naught is already 0, so this is 0, that's good. But b1 is the second term, and here that 1 here is your b1. So this is going to be 1. So this is going to be 1. So your second variable is going to be y dot minus u, actually. You're combining the input and the velocity together. Okay? So your first one, x1 is y, x2 is y dot minus u. And if you do that, then your A matrix, you can easily show that your A matrix will be the first row, okay, 0 and 1, and then your last row still negative an and negative an minus 1. So since here I have leading term of 1, that makes life easy for me. See if I can make my pen right. So this is an and this is an minus 1. So negative 3 and negative 2. So that is my A. Then my B is going to be beta 1 and beta 2. Beta 1 I already calculated. Beta 1 was 1, so I write it. but I also need to calculate a beta 2, which I didn't, but I can go ahead and calculate that. So there's going to be 1. Now, beta 2, as I said, I have to calculate, and I will do that. Then I have my C. Now, for some reason, my pen doesn't want to write. C is simply 1 and 0. And D is simply beta naught, which in this case is 0. So the only thing I need to find is the second entry of B, which is beta 2. And beta 2 is B2 minus A1, B1, beta 1, A2 beta naught. So beta naught is 0. That makes life easy for me. So the last term is 0. So this guy is 0. Beta 1 I calculated, that's 1 A1 here, right? This is A2 because n is 2. So this is A2, this is what? A1. A1 is 2. Beta 1 is 2. So if I calculate it here, beta 2 is going to be B2. This is B2. It's going to be 1 minus A1, which was 2, times beta 1, which was 1. Then minus A2, 3 times beta naught, 0. So if you calculate it, that is going to be negative 1. So I plug it here. Okay, so with those choices, with this choice of y to be my first state vector and the second one to be y dot minus u, this is my state vector, then I can show that, and I'll leave it up to you to prove that. I can, if I take a time derivative and write it based on everything else, then I can have my A, B, C, and D to be these matrices. Okay, so I got that one done. So now I know how to go back and forth between all of them. The last thing, since I have a little bit time, I would rather finish the whole thing, is linearization of nonlinear state space equations, because this is actually very fast. But you know what? Before I go to that, let me show you relevant MATLAB commands, because that is useful. So remember, in the past, if you had a numerator and a denominator, you could create a transfer function, and then once you have a transfer function in MATLAB, you can do a ton of more things, okay, which we'll go through and I'll show you. You can look at the step behavior, you can look at impulse behavior, you can do ILAP, you can do so many things. So one thing we have done in the past was, let's, for the example that we solved, the mass spring damper, we go with M of 1 and then K of 5 and then B of 2, okay? So if I choose these guys, then my transfer function G will be TF of, numerator was 1, denominator was ms squared, so 1 plus b and k. So this is the transfer function I found using numerator and denominator and the command tf, correct? Now, I showed you that the matrices A, B, C, D, for this case, they were 0 and 1, and then you had negative k over m and negative b over m. So this was A, B was basically 0 and 1 over m, C was 1 and 0, and D was simply 0. Yes? Now, can I use these A, B, C, D matrices and basically create a transfer, a system using these matrices? Can I create the same system that I showed with this transfer function? can I create a system equivalent to that, but using these matrices instead of numerator and denominator? Yes, in MATLAB, the command to use is called SS, state space. So I say my system, if you want, I can call it, let me call this G1 if you don't mind. So, oh, big mistake. Should just clear G. That's fine. So G1 is the one that is defined by transfer function. Now G2, I do it with A, B, C, and D, and the command SS. Now when you do it with command SS, do not expect the transfer function back. You will get a system G2, but that G2 will be displayed in the state space manner. Now I want to see if the behavior of these two systems is the same if I give them the same input. So I use the command step and I say, what is the step of G1? Show me the step of system G1, the one with transfer function. And that's the step, right? Now I say, give me a figure, a new figure, and in the new figure, you give me a step of system 2. Let's see. What do you say? Identical, right? Yes, it is, because they are the same system. So it doesn't matter if I define my system by using matrices A, B, C, D, or if I define it using a transfer function. The response is going to be the same because they are the same system. Now, if I have a numerator and a denominator, can I get matrices A, B, C, D? Right? Basically this guy, right? I'm going from a transfer function to state space. Can I do that? Yes, MATLAB can do that for you. Just pass it numerator and denominator. MATLAB will give you what? A, B, C, and D. So let's do that here to see. So I call them A1, B1, C1, and D1 so that I don't mix them with those ABCDs. The numerator was 1, I guess, and the denominator was 1, 2, and 5, right, for G1. Look. Are these the same as those ABCs that I defined? No. That's quite interesting, isn't it? Look at A and A1. I expect the same thing, but they are not. But they are like the rows are just swapped, right? And look at B and B1. This is B, this is B1. Look at C and C1. Yes. They are very similar except for the elements are exchanged. Do you know why? So as I said, when you go from transfer function to state space, there are infinitely many solutions. And this one that MATLAB provided is also canonical. But the only difference here with the one we found is the order of the states is reversed. So MATLAB, we chose what? We chose our state vector. We chose our state vector to be what? Y and Y dot, that's what we chose. But you know what MATLAB chose? Yes, you are right. It used Y dot and Y. It just reversed the order. And if you do it, then all of those rows and elements of ABC will be swapped. D is 0, so nothing would happen to it in this case. Okay? Still canonical, but just swapped. So don't be surprised if MATLAB gives you something that is not identical to what you found on the paper, okay? There are infinitely many solutions when you go in this direction. Now, if I have my ABCD, can I get my numerator and denominator back? So I want to go backwards. I want to go from state space to transfer. In other words, I want to implement this formula. Can I get a numerator and a denominator? Yes, and this time it should be unique solution. So regardless of which one of those A, B, C, or A1, B1, C1, D1 I use, the result should not be any different. So take a look here. One time I use A, B, C, D, and I get my numerator and denominator, yes. The other time I use the swapped version of A, B, C, D's. And look, the same thing. Right? The numerators are the same, denominators are the same. So this is unique this way is not. Okay, so I guess now we are in good shape about that. Let me just go very fast through this guy here and finish up this whole thing. So here, what I need to do is, remember that when you do state space method, you can write it even for nonlinear functions, right? So f and g are in general nonlinear functions. Now, there are scenarios that, because for linear systems, when we have linear equations like this, analysis and design of control is quite well established, and we exactly know what to do. If we have a linear system, we can analyze them, we can design controller for them very easily, and it's well established. We have all sorts of nice, good, fancy formulas. But when it comes to nonlinear systems, actually it is very hard. Okay, there are not always a solution, and it's not going to be super easy, convenient. So one of the methods they do in controls is linearization. They say if these functions f and g, which are nonlinear, are only evaluated at a small range of x and y and t as they change, okay? So you just look at these functions around an operating point, basically. Then I can, around that point in a small range of u and x, I can say these functions are what? Almost linear. I can approximate these nonlinear ones by what? By a linear function. And when I can say they are linear, then I can apply all of those good development formulas that I have for linear systems. Now, what if my system operating point moves from the current point to next point? Well, again, I will linearize the system around the new next point, and then new and new and new. So basically, you have several criteria, right? Let me show you what I mean. So let's say this is just one function, nonlinear f of x. And this is x. Let's say there is no u, just f of x. And this function is nonlinear. So I say if I'm in here, if I'm at the moment x is here, I just look around what? This current operating point. So let's say at the moment, I'm just limited to this area. In this area, I can say the function is well approximated by a line. So I can approximate my function f and my function g around this point and behave and control the system using the formulas for linear systems. Now, if my system moves from that point and comes here, now I linearize it again in the neighborhood of this point. So now I will focus here only. So I have now new control law for there. If I come here, I do it here, okay? And so on and so forth. So you do not have basically one control law for the whole system. Each point has its own control law. So this is one of the common methods for controlling nonlinear systems, okay? And that's why we need to know at this point, although we might not be really using it much, but it's good for us to just learn that sometimes it's a good idea to linearize a nonlinear system. And all we need to do is to use the Taylor series, which you learn in your calculus. That's another application of Taylor series in engineering. So if it has one single variable, your function, then use the Taylor series for one variable function, and you see the Taylor series goes forever, but if you want linear function, you just use the first two terms. If it's multivariable, let's say two variables here, then you only use what? The first three terms, the constant term and the two linear terms, correct? And then you linearize the system. Okay, so if it's three variables, then you have three linear terms and one, so you have four terms. So let me just go through this example here very fast. So if you have a nonlinear function z, and this z is a function of two variables, x squared plus y squared. So the surface of the nonlinear function z equal x squared plus y squared looks like this green surface. Now I want to know around the point, operating point of x of 1 and y of 1, which is here, can I approximate it by a linear function? So in 3D, linear means what? A plane. Can I approximate that curve by a plane around an operating point? And the answer is yes. Now what's the equation of that plane? We'll find it. So what I have here is z to be x squared plus y squared, and your operating point is at 1 and 1. So I use the Taylor series for two variables, which is this bottom guy here, and I only use the first two terms, right? So I can use this one if you want. And I write it here separately. So I say this is approximated by the value of this function. If I call this f of x and y, okay, this is a function of two variables. It is going to be this function evaluated at the nominal point, the operating point, plus. And you can see the two linear terms. Partial derivative of f with respect to x1. Actually, these should be partial derivative, not direct derivative. So let me fix it before I forget, because it is really important that you do correct notations. So partial derivative of f with respect to x1 calculated at the operating point multiplied by x minus x bar. So partial derivative of f with respect to x here calculated at this point multiplied by x minus x bar, and then a similar term for the y. Now here I will find my partial derivative. So partial of f with respect to x is 2x. Partial of f with respect to y is 2y. So this guy is just 2x. And this guy is 2y. So if I do that, what do I get? So if I calculate the function at 1 and 1, clearly it gives you 2. And then 2x at x equal 1, so that is going to be 2 times x minus 1, and that is going to be plus 2 times y minus 1. And if you simplify it, it is going to be what? 2x plus 2y minus 2. So I say this function can be approximated by, this nonlinear one can be approximated by this linear one around what? Around this point. Around this point, the value of these two guys are very similar, okay? And you can check it. For example, if you plug in 1.1 and for y you say like 0.9, if you calculate the exact value and if you calculate the approximated value, you see they should be quite close to each other, right? So 0.9 squared plus 1.1 squared is 2.02. And then this one is going to be 2.2 plus 1.8 minus 2, so that is 2. So this is going to be 2. So they are not exactly equal, this approximation, but the approximation is relatively good, okay? It's just 1% difference. And you can see that here too, that only around that point the plane is tangent to the surface and close to it. Once you get away from that point, then the gap between the actual and the approximation gets what? Large. But around that, the two surfaces are actually very similar to each other, and here I did it using MATLAB, right? So I plotted them, I did the nonlinear function, I did the linear function, and I used the mesh command and put the meshes on the top of each other so that you can visualize it. Okay, thank you so much for your attention. I'll see you in the next lecture.